Okay, so good morning, everyone, and I will thank you organizers first for having me here talk in front of this quite big audience today. I think we're doubling the numbers of last year. I'm Claudio Zeni. I'm a PhD student at King's College London, and I'm working with my group and Professor Alessandro De Vita on efficient n-body machine learning force fields. So.
That requires USB.
Oh, okay. I just use it. So, well, Professor York-Beller already talked about this, but again, a brief reasoning on why we use machine learning. Well, we want to have good accuracy on forces and energy on systems that are too big to use DFT on, or precise methods. So what we do is we construct a DFT database, and then we train the machine learning algorithm. Of course, constructing the DFT database is expensive, so we would like to do it in the smallest size possible. So, once we have our machine learning algorithm, we use it to predict forces and energy on our system. One of the problems is that while faster than DFT, these machine learning algorithms are quite not as fast as classical force fields. Thus, their application is still limited to some particular problems. What we are working on is, and we are working on a software package for it, is this mapping algorithm that allows us to use a machine learning, a trained machine learning, in particular a Gaussian process, and map it onto a grid of values to increase its speed almost to the limits of classical force field. So, a brief introduction to what we use. We apply Gaussian process regression for our machine learning algorithm. We start from a DFT training dataset. In our cases, we work with forces, we can work with energies, and we basically use the positions of atoms in a local neighborhood to describe the system. So we have a cutoff radius, RC, and basically what we do is we predict forces or energies on a target configuration based on the database. This is done in Gaussian process regression to the optimization of the weight vectors, alphas. This is done using simple least square regression. And what we focus what Gaussian process is based on, and is nothing but a very fancy name for a similarity function that compares local environments and basically predicts the value of forces or energies. A nice feature of Gaussian process regression is that an uncertainty value can be associated to predictions, so we can know when we are far away from a database interpolation and we are prone to errors. Another interesting feature is that Gaussian process regression only contains a very small number of physically meaningful parameters. So we will not spend time tuning them, as they are very easy to fit and, as said, are physically meaningful. So they're very easy to interpret once we train it. So a few words on the kernel function. As said, this is a similarity function. Well, first of all, we need to represent the atomic environment. There are many choices possible. One of the most widespread ones in Gaussian process field is the SOAP, the smooth overlap of atomic potential. We see one of the expression there. So the environment of an atom is expressed as a sum of Gaussians centered around each atom in the neighborhood. But there are others representations which are also valid. For example, we can use a set of distances, a set of angles. The choice depends on the kernel function. This kernel function, as already said, should be invariant to permutations, translations, and rotations of the system, because if we rotate the system, the energy does not change. The force changes covariantly, so if we rotate the system, the force rotates accordingly. Moreover, we want to enforce energy conservation. If we are training on forces, this is fundamental. We do so by using a derivative kernel. So what we do is we first define a kernel on energies and then double derivative to obtain a energy conserving kernel on forces, for example. And the last but very important feature of a kernel is its order. This is the maximum number of simultaneously interacting particles it can describe. For example, a two-body kernel works only as a function of distances from the central atom, and thus will not be able to distinguish between configurations which only have angular differences. We went through a procedure to construct n-body kernels. So once you have a representation of your environment, for example, distances or angles, you can easily construct an n-body kernel, which is invariant with respect to the permutation, translation, and rotation, simply by comparing the bonds, bond distances, if we are talking about a two-body kernel, or angles or triplets, if we are talking about a three-body kernel. Once a kernel is defined, another kernel can be constructed through simple elevation to a power. So if we have a two-body kernel, for example, we can easily construct a three-body kernel, simply raising it to the second power, so squaring it. These extend to any order. And of course, many-body kernels, many-body means that the kernel can distinguish between any number of simultaneously interacting particles in the environment. These are the only ones that are universal approximators, so that can learn indefinitely and can reach perfect accuracy. And these can be obtained through normalization, as done, for example, in the gap potentials, or through exponentiation of an n-body kernel. Of course, there is a price we pay for higher order. We get more accuracy because we can distinguish between environments that maybe two-body kernels see as the same, but we need more training points because the dimensionality of the problem increases. For example, if we have a two-body kernel, the only dimensionality we care is the distance. So it's a very simple to train kernel. Moreover, we have slower computation because as a two-body kernel goes with the number of neighbors, a three-body kernel goes with the square of the number of neighbors because we have to account for every triplet in the system. So it is fundamental to choose the right n for the task. If we look at training on baud nickel, for example, we can see easily that the green line, the two-body kernel, reaches accuracy very fast with approximately 50 training points. This is the error on forces, by the way. And this accuracy is basically capped with the two-body kernel. The three-body kernel does not increase its resolution. The error goes down by 5%. And the many-body kernel also reaches this value. Eventually, it will reach 0, or the value dependent on the cutoff used for the carving. But, of course, the many-body kernel is much slower. So if, for example, we look at bulk nickel, the sensible choice is to use a two-body kernel, because that's enough, and it's much faster. If you go to more complex environments, of course, the two-body kernel cannot reach an adequate accuracy, so we have to use, for example, a three-body kernel. A nice feature of this mindset about n-body kernels is that we can use the relative accuracy to distinguish, to define our environmental complexity. For example, we see in the insets that both nickel has a constant accuracy plateau for every order n, but the clusters, which we will talk about later on in this presentation, have an accuracy that depends strongly on it. So the cluster is a much more complex environment. This holds the same for crystal and amorphous silicon, by the way. Okay, so a brief formal discussion about this mapping procedure. It's a bit maybe heavy, but it's interesting to look at. So if we have an n-body kernel, not a many-body kernel, see n-body kernel with n infinite, we can expand the kernel function into two n-1 nested sums of a function g. Let's call it just g. So we have that the kernel is a sum of n-1 atoms in the target configuration, m-1 atoms in the training configuration of a function. if you apply the kernel definition and then we swap the sums, we have that the prediction on a target configuration row, for example, of an energy, but this can also be a force or any other property really, is given by a sum of all the contributions up to n-1 order in row, and a function that only depends on the training set. So this function is fixed once the algorithm is trained. So we can just call it a function h, and we have that the prediction on a configuration row is just a sum over all the n-1 plets of configuration row of a function. This function h basically maps every n-plet to its machine learning predicted energy value or force value. But in our case, we used energy values. So what we do is just we store this array of values. For example, if the kernel we use is a two-body kernel, this is simply a set of distances. We just store the value for every distance between the minimum and the cutoff. In the case of a three-body kernel, this is a cube basically of distances. So we have for every triplet, we have the R1, R2, and R12. And once we have done this, we basically forget about the whole Gaussian process, the whole machine learning, and we use this as if it were a classical potential. For every value of a triplet, we associate an energy, and we can simply use spline interpolation to get all the values, and we can get the forces simply derivating the spline. So what we get at the end is a non-parametrical, n-body, classical-like force field. This has the advantage to being much faster than the Gaussian process. For example, we get 10 to the 4, 10 to the 5 speed increase with sensible number of neighbors, local neighbors, and training points. So, for example, for 1,000 training points, which is very sensible, and 20 neighbors, yeah, we get basically 10 to the 4 speed up. And this is done without much accuracy loss. We see that for a grid, this is for a three-body kernel and 1,000,000 training points, we only lose 0.1 milli-electron-volt per angstrom. So we lose less than 1% of accuracy, 0.1% of accuracy. So basically what we get is the real Gaussian process, just much faster. So we're done with that theory. We'll now talk briefly about a recent project we were involved in. We were looking at machine learning force fields for nickel-19 nanoclusters. The 5 structures we looked at that you can see on the column on the left. And we looked at this because, of course, nanoclusters are very interesting for catalysis. And DFT calculations are very useful, of course, but are limited to the time scales they can reach. With this mapping procedure, we managed to simulate a melting with rates that were not accessible to DFT before, and we almost reached the microsecond limit. We are talking about hundreds of nanoseconds without much computational effort. First, we looked at the system. Of course, when you train a Gaussian process or any machine learning, you really want to optimize your training database. It has to be as small as possible because every calculation requires additional DFT computations. So up to the limit where it is not useful anymore to create a Gaussian process if you already have all the DFT data, and also to get more understanding about the system. Of course, training sets that contain multiple morphologies provide better accuracy, and in the case of n-body kernels, you must ensure yourself to sample the local environments well. So for a two-body kernel, you want to get all the values of distances, possibly. For a three-body kernel, you want to get all the values of triplet distances, or two distances at one angle. You want to span it as much as possible. Because at the end of the day, if you fill out your space, our cube in the case of three-body kernel, you're not interpolating really anymore. You're not extrapolating really anymore. You're always interpolating. Because you recast everything as a two-body or a three-body function. So, for example, we trained a database on 300 Kelvin configurations, and with 500 training points, and we got very good accuracy on low temperature structures. So, on the limit of 0.1 electron-volt per angstrom. You can see it here. This is the low temperature configuration, low temperature training set. And decent accuracy on high temperature structures. We are looking at 0.225 electron-volt per angstrom. When we talk about high T, we talk about 900 Kelvin, where this nanocluster starts to melt. Is liquid-like. Of course, the inclusion of high temperature structures improves accuracy, both at low temperature and high temperature. But this is a paid price, because, of course, if we include the high temperature structure, it means that we calculated them through DFT. So we would like to avoid this. And we, for example, at 100 training points with both IT and low T function structure, we get a very nice error on forces and a good error on energies. We have to remark this. We are training only on forces, so the prediction on energies is only given by the force predictions. There are no energy prediction in the training datasets. Energy values, sorry. So, to get a first glimpse of what we can do with this, we try to melt the system. We ran 4 repetitions of 19 simulations for all of the 5 morphology studies. And we looked at the root mean bond fluctuation. This is a quantity used in nanocluster science to determine where a nanocluster is liquid-like or melting. Okay, thank you. The total simulation time was approximately 200 nanoseconds, and the speed was 440,000 steps per hour per core, so quite a good speed. And this is the result we obtained with the low temperature training set. And what we see is that we see that the nanocluster displays liquid-like behavior above 1000 Kelvin and is in a slush-like region between 600 and 900 Kelvin. Then we went back, and as I said, we trained the database on high temperature structures to see if the behavior changed. And this is what we got. So we see that we get quite good accuracy even without the high temperature structures, and the slush-like behavior is still between 600 and 900 Kelvin, and the liquid-like behavior is always also above 1000. So we get similar results even without training on high temperature structure. This is very promising because it means that we don't have to do the DFT calculations to get to these accuracy results even at high temperatures. So, brief summary. We presented a way to systematically build invariant and energy conserving and body force fields, and we demonstrated that we can construct parameter-free and body force fields using this mapping procedure. And this mapping procedure brings the GP to be almost as fast as classical force fields. We are currently developing a Python package for this, which also will contain the following improvements. So we will implement multi-element 2-entry body GPA mapping, which is not showcased here. And we will include joint force and energy training, of course, to improve the energy accuracy, because we saw the energy accuracy was good, but not very good. And at the end, we will insert this watchdog feature using the GP predicted error to see where basically we don't know, to get an alert where the mapping force field can tell us where we are predicting something wrong. Okay, thank you for the attention. We thank the team and the funding and support. Thank you very much.
So, very short time for question. Alan?
Yeah, I guess you addressed it, so maybe just to be clear, you were melting the small clusters?
Yes.
Which I guess is not really your long-term aim, is to do something more experimentally relevant. And then this energy is going to be a big problem. I mean, this 10 millieVs per atom, if you have 1,000 atoms, how would you even judge what structure you should have with this sort of accuracy?
Well, the accuracy problem is, the energy accuracy problem is definitely a problem. Well, addressing it would be quite straightforward because we will just use energy as energy in the training set. We're not using it now.
I'm asking this because we have exactly the same problem. That we're trying to use this type of approach to predict morphology in large clusters. And even when we get down to 1 milliev per atom, it's not good enough if you have a big cluster. So I'm just, maybe this is something for later, like how we can improve this, even when we are training on energies.
Okay, we haven't looked at this, to be honest. We used the system that we had available and we tested on it, basically.
I mean, this works very nicely.
Yeah, but that's definitely interesting, and we should definitely discuss later on this. Yeah, but thank you for the question.
Yeah, so I'd just like to point out that actually this mapping is not dependent on the Gaussian approximation potential, because by definition, whenever you have a machine-fitted, machine-learned potential, that's a function that goes from the input parameters to the output parameters, and so you can just do a spline interpolation of that. Just build a grid and then do the interpolation. But the thing is that then you have to have a very low dimensional data set, because otherwise your function table is going to be too big. So actually calculating the potential straight from the input equations is going to be faster. And then the second part was that, so your lab results on the liquid. So because your initial data looked rather converged. So next slide. Yeah, so this is converged at high temperature, but then when you do the refit, I fail to see that it is actually converging anywhere. So do you have a comment on that?
Well, this is very preliminary results because we finished the calculations 2 days ago, basically, and we only did 3 repetitions of it. We believe that with more repetitions, there will be a tighter convergence of it. And also, even if we are working with relatively slow heating rates, they're still too fast to get. They're still fast enough that we have an uncertainty on the actual temperature range. So you can look at the data and think about plus minus 30 Kelvin on every point, and that is given simply by the heating rate. So yeah, we actually believe that this will converge. Well, this is already converging nicely, and will converge in an even tighter way with longer simulations and more repetitions.
Okay, sorry, we have to move on. And let's thank the speaker for providing a very cleanly commented and very well documented Python code as well.